Hello everyone. In the previous video, we've seen a two approximation algorithm for the TSP problem, traveling salesman problem. Today I'm going to finish the series with the Christofides algorithm, which is a 3.5 sort of 3/2 approximation algorithm. This means that this algorithm, in the worst case scenario, it finds an Hamiltonian cycle that is as I said, in the worst case, 3.5 times worse than the optimal tour, and than the optimal cycle. Okay, so if you haven't seen the two approximation algorithm video, I strongly recommend you to watch it because this algorithm takes a lot of ideas from the previous one. Okay, so the first step in the algorithm is, as always, finding T star minimum spanning tree of G, and I'm going to draw this right here. So this can be our spanning tree, and as always, this is an operation that you can do in polynomial time, and so it doesn't affect our overall computational cost. So we can do this how many times we want. Okay, so then the second step is kind of different from before. So if you remember, in the previous algorithm, what we did was creating an extra edge for every pair of nodes, so something like that. So this is what the two approximation algorithm does. So with Christofides, we do something a little bit smarter, to do a little bit less work. And I'm going to show you now what I mean. So in Christofides, what we do is we select the edges, the nodes which have an odd degree. In this case, these nodes are these ones. So obviously all of the leaves, and also this guy, and also this guy. So these are nodes that have odd degree, so they have an odd number of connections. And as we can see here, this is, so we selected 6 nodes, and this is not a coincidence. It turns out that every time in a spanning tree, when we select the nodes with odd degree, we will end up with an even number of nodes. This is something that we're going to prove later, but for now, just take it as it is. So we have an even number of nodes which have odd degree. So now what we want to do is we would like to transform, to basically make these nodes have an even degree, not an odd degree anymore, because with an even degree, we can find an Eulerian tour and then do the same things as before. So then we can find the Hamiltonian cycle with the shortcuts. So in this case, what we do is we find what is called a perfect match. And we're going to call E star on G prime. So we will call this thing G prime. So what is a perfect match? A perfect match is, so let's first define what a match is. So what a match is? So a match is basically a set of edges, something like that. So it is a set of edges which covers all of the nodes of our graph. And basically I have, these edges are non-overlapping, so there is no node that is in common between different edges belonging to the match. So this is an informal definition, but I hope it gives you the idea. Okay, so remember, here I've drawn the spanning tree, but our graph is complete, so we will for sure have those edges. So in this case, for example, it might be something like this. Sorry, no, this is not possible. So it's something like this. So in this case, as you can see, this is a perfect match because this is a set of edges that covers all of the nodes of our graph and the edges are non-overlapping. So I will erase this part here, hoping that you understood what a match is. And now, what is a perfect match? The perfect match basically is just the match with minimum cost. So among all of the perfect, or among all of the matches, this is this one that we selected is the one that minimizes the cost of the edges. Okay, so now, as you can see, all of these nodes that we created have an even degree. So what we can do, so these guys have even degree now, this other guy had an even degree also before. So what we can do now is find a Eulerian tour on what? On basically T star plus A star. So we take the old spanning tree, add these edges that we found of the perfect match, and we find an Eulerian tour on that, and we call this E. And then fourth step is just find Hamiltonian cycle by using shortcuts. So I've already explained what a shortcut is in the previous video, but in case you're here only now, basically our Eulerian tour might tell us, for example, go here through this edge, then go here, go there, and just go back to the origin. So the only problem with this is that we might visit a node more than once. So with an Eulerian tour, we visit all of the edges exactly once, but we might visit the nodes more than once. And with shortcut, I mean, like, let's say we go there, then we go here, then we go here. So we just follow this path. Now, when we are in this point, so when we're here, when we are here and we should go back there, basically we can detect that this is a node that we have already visited. And so instead of doing this, what we do is we take a shortcut and go here. And then from here, we can just take another shortcut and go back here at the beginning. So a thing that I haven't said at the beginning of the video is that because of this thing with the shortcuts, an extra assumption that we make is that for each U, V, and Z, we have that the cost of going from U to Z is lesser or equal than the cost from going to U to V plus the cost of going from V to Z. And this is something that we assumed also for the two approximation algorithm, and in this case it's exactly the same, because we want to say that this Hamiltonian cycle that we found, we call this H, we want to say that this H, the cost of H is less than the cost, lesser or equal than the cost of E. And this is something that we want to say in our proof, so that's why we assume this thing. Okay, so this is the algorithm. It's not very hard, and now we get to the proofs. So I'm going to erase this part here. Maybe leave the drawing. So let's start with the first proof, which is proving that the number of nodes with an odd degree is always an even number. So the theorem says the cardinality of basically, well, we can say, I'm thinking about how to write it formally, but the cardinality of S, where S is the set of nodes, so V in T star, such that DAG of V is an even number, so is an odd number, I mean. So given this S, we want to prove that, so we can say given this thing, so the set of, it is a set of nodes belonging to T star, so actually nodes in our graph, we can say. So let's just put G here, nodes in our graph, where the degree of that node is odd. We want to prove that the cardinality of S divided by 2 is equal to 0, modulo 2 is equal to 0. So how to prove that? So if we take the summation for every node in our vertex, in our vertices, and we sum the degree of that node, this thing will for sure be twice the number of edges in our graph. And this is something that you should learn if you're doing, if you're analyzing this sort of algorithms in an undirected graph. This is always true. So the summation of the degree for each node is always twice as the number of edges that you have in the graph. So we can see that this is obviously an even number, because any number multiplied by 2 is even. And now what we can say is, let's try, instead of iterating on all of the nodes, let's iterate on the nodes belonging to the vertices where the DAG of V modulo 2 is 0. So we are iterating on the nodes with an even degree. And we do the same for the nodes with an odd degree. DAG of V modulo 2 this time is different from 0. And we still sum the DAG of V. We know that this thing is an even number. Okay, so if we look at this equation carefully, we can see that here we are summing even numbers. And for sure, a sum of even numbers will for sure be even. So this thing is even. So now we have an even number plus something has to be an even number. It means that this number has to be even as well. Okay, so this is what we are observing. And if this, so this summation has to be even. But here, remember that we are summing numbers which are odd. So so we can ask ourselves when, like, if I sum an odd number, like if I sum odd numbers and I want to get an even number, it means that I summed an even number of odd numbers. It means that here, so we're gonna write it for sure. I summed an even number of odd numbers. And this is what we wanted to prove. So we proved that the number of nodes with an odd degree is an even number. Okay, so that's it. Okay, so for the second proof, what we're going to prove is that the cost of H divided by the cost of H star is always lesser or equal than 3 over 2. Okay, so this is what we want to prove. Okay, so the first thing that we, as the other time, we have to sort of write down some things that we know about the graph and about how we sort of constructed this algorithm, and then try to put together all of the equations and get our constraint. So in this case, what we know is that for sure the cost of the Eulerian tour, so of E, is for sure the cost of E star, so the perfect match, plus the cost of T star. Because we built the Eulerian tour going around the original spanning tree, and we added these edges belonging to the perfect match. Plus, another thing that we can say is that for sure the cost of E is greater or equal than the cost of H, because we use shortcuts and because we have this assumption here. Then, as the other time, as in the two approximation algorithm, what we do is we can say this. So let's assume that this is our optimal Hamiltonian tour H star. If we remove an edge from here, then we obtain a generic spanning tree T, and we are sure that the cost of H star is greater or equal than the cost of T, because we obtained T by removing an edge, and by removing an edge from H star, and then we know that this is obviously greater or equal than the cost of T star. And this part is pretty similar to the two approximation algorithm. So now, the thing that Christofides came up with is the following. So if from here we take the nodes, we select the nodes that we selected here in the spanning tree, so the ones with which have a odd degree in the spanning tree. So these nodes, let's say that they are these nodes right here. We can, and let's now find an Hamiltonian tour on these nodes. So for example, this one. Okay. And let's sort of reproduce it down here. We can see this specific Hamiltonian tour as a combination of two matches. So, for example, this is a match, and this is another match. So we call this thing gamma. So the tour we call the tour gamma. We have that the cost of gamma is for sure equal to the cost of M1 plus the cost of M2, where M1 and M2 are these matching here. Because as you can see, those are valid matches because they are edges that are non-overlapping, so they don't like none of the nodes are belong to two different edges, and they cover all of the nodes in the tour in the graph. So they are valid. They're valid matches. So what we can the cool thing now is that we can say that the cost of M1 plus the cost of M2 is for sure greater or equal than twice the cost of E star. And this is because E star was our the perfect match. It was our minimum cost match. And this statement has to be true because otherwise it means that either M1 or either M2 is greater, like the cost of one of these two will be smaller than the cost of E star, but it is impossible because we built E star so that it was the minimum cost match. So this is something that we can say. And for sure, this stuff here is compared to the cost of our optimal, so cost of H star will for sure be greater or equal than this stuff here, because we basically removed some edges from the optimal H star. Okay, so now we are ready to put together things. So what we can state from this is that the cost of H star is divided by 2 is greater or equal than the cost of E star. And now we can say that the cost of H is for sure lesser equal than the cost of S star plus the cost of T star, and this is by just substituting this cost of H in here. And then now we can put this is for sure bigger than this, so we can substitute this here without changing the sign here. And the cost of T star, we can for sure put something that is bigger than the cost of T star and still keep the sign unchanged. So cost of H is lesser equal than the cost of H star divided by 2 plus the cost of H star. And this means that the cost of H will for sure be smaller than 3/2 cost of H star. And this is what we wanted to prove. So we are sure that in the worst case, our solution is at most 3.5 times bigger than the optimal solution. So also in this case, we can do a tightness analysis, but it's kind of artificial and complicated. Maybe I will tackle it in a later video. Thanks for watching.